have movement along faults, usually what ends up resulting are earthquakes. So we have to look at first what an earthquake actually is. And basically what it is when the crust, we've talked about how it moves along the transform faults. Well, when it's moving, it doesn't move all at once. It doesn't, like, it's, imagine if you're pushing your hands together and you're pushing and you're pushing and pushing, and all of a sudden there's a sharp movement like your hand slips. That's kind of what happens with earthquakes. The pieces of crust are pushed up against one another, and there's that pressure as they're getting compressed together, and they're sliding along one another. They move just a slight bit, and then when actually the breakage happens and it moves, that produces vibrations. And those vibrations move out from the center point of wherever the break originated at, and that's what we call the epicenter. And those vibrations are what actually cause the damage, and that's the shaking that we feel. So you have on here, you see, here's your focus. This is where the movement actually happened. And then above that is where we actually feel it. And so when they say this is where the epicenter was, what they're talking about is where we are on the ground. So where the breakage is happening is called the focus. Down here, okay, epicenter is above that. Here's again, so you can see it along the fault line. And usually you can see on here that the epicenter doesn't necessarily happen right where the fault is. Okay, it's happening above where the breakage actually happened. So you can see here's your fault line right here, and we've got the wave moving out from here. And this is called, remember you looked at your different kinds of stress, okay, with your tension, compression, and shearing, and this is shearing that's happening. Okay, which is the stretching or pulling. This is a normal fault. This is happening at a divergent boundary. Kind of impressive, huh? Okay, now you can look at, see, remember in the other one you looked at, you see how it's kind of squished up like this? Okay, it's getting pushed together. And so this one, remember, this is our hanging wall and our foot wall. Hanging wall is getting pushed up, which makes it compression, so it's happening at a convergent boundary. And we get a reverse fault. And there's a reverse fault. So you can see, here was your hanging wall. This is your foot wall. And it's displaced over the top of it. Also very impressive here. You can see, it's a lot easier to see it from the side than it is to see it from the top view, like what you were just looking at. Here's your fault line coming up here. Hanging wall, foot wall, hanging wall's moved up. Okay, this is a picture of the San Andreas Fault right here. So we know this is shearing, so it's that side-to-side motion. And it makes a strike-slip fault. And there you can see, so this was all straight at one point in time. I wouldn't want to take my train on there now. So you can have that release of energy because of the movement happening, but you can also get earthquakes for other reasons. And this is why a lot of times before a volcanic eruption, you'll have an earthquake. Mount St. Helens, when it erupted the last time in 1980, was preceded by a series of earthquakes because the magma was moving up from the magma chamber up through the earth, and that actually caused the shaking to happen. This is the San Andreas Fault again. So when you have a major earthquake, it's not that you're having, it's not that the foreshocks are like little it's more like they're little tremors, but they're smaller earthquakes, but they're separate. It's a separate incident. This is where the crust slipped a little bit and the earth shook. So a foreshock and an aftershock are still earthquakes. They're still slipping happening along the fault line, but they're just not the 7.0 necessarily, or they're not the biggest one. Usually they call the biggest one is the earthquake, and the little ones that happen before that are the foreshocks, and the ones that happen after that are the aftershocks. They can cause a lot of damage. Here you can see, here's your plates moving side to side. This is where the actual breakage happened. You'll have right above that is where you feel it the most. So we have 3 different types of seismic waves, and basically this is just how the energy is moving through the planet. And we looked at this a little bit before, and people ask me, well, how do we know what our core is made out of and what our mantle is made out of? And one of the reasons we know this is because of our types of seismic waves. Because these waves, some of them can move through everything, and some of them can only move through liquids, and some of them can only move through solids. And so by mapping around the world at seismograph stations where they feel these waves get there, we can kind of get an idea of what the center of the planet is like. So the first one we're going to talk about are P waves. They're the primary waves. They move the fastest. They go through everything on here, and they're usually not the ones that cause the damage to anything, but they are the waves that we feel the first. The next kind of wave are the S waves. They're slower, and they can go through solids, and you can see that's SSS. So S waves, slow, solids, also not causing damage. The ones that actually cause the damage are the L waves. These are the ones that kind of roll across the ground. They're the slowest out of all of the waves, so they're even slower than the S waves. But these are the ones that cause all the damage because they're rolling really slowly. They're happening right along the surface of the ground. And here's pictures of them. You're not going to have to be able to identify them from pictures, but you will want to know how fast they move and which ones are causing damage. So we measure earthquakes using a seismograph. And what you're looking at right now, the picture on the left here, this is the seismograph. This is the actual machine. And this is the seismogram. And that's the report, basically, that it prints out, or the lines as it's recording how it's moving. We measure 2 different things about the earthquake. We measure its intensity, and we measure its magnitude. And the intensity is when we look at how much damage did it do. Did it knock down buildings? Did it just shake the ground? Did it move the trees? That sort of a thing. That's when we look at intensity. The magnitude is the same whether there's buildings there or it's flat ground. We're looking at the amount of energy that's released, and that's not contingent upon what's there. The intensity depends on basically what's there. And it can knock down buildings, but what if you have to look at, what are the buildings made of, and were they made to the right protection levels and that sort of thing for earthquakes. So one of the scales is called the Richter scale. This is measuring the amplitude of the actual waves. So this one's measuring the magnitude, or the amount of energy, not the intensity. And here's an example of what it looks like. When we're looking at where an earthquake is at, we're going to look at where the epicenter is at, and then we can figure that out by how long it takes for the P waves and the S waves to actually get there. And usually they find it in 2 to 3 stations, and then they can kind of figure out where that intersects, and they can figure out where the epicenter is from there. here's an example of that. So you have 3 different seismograph stations. They're measuring the arrival times, and where those arrival times intersect is where the actual earthquake occurred. So how does that tell us about the structure of the Earth? Well, the waves travel at different speeds, and so when they slow down, for example, in the where the arrow is pointing to right here, we know that the core and the mantle are made out of 2 different things, solid and liquid. And so we know that when that change in speed happens, that we're actually looking at a change in the material that it's going through. They move slower through solids on here, and they can move faster than through liquids. So most of the dangers that happen are not because of the earthquake itself, like the earth cracking open and people falling into it or anything like that that you see in the disaster movies, but it's usually from being inside of a building and something falling, or being close to a building and something falling, broken glass, that sort of a thing, or from fires. Now, a tsunami is a little bit different than that because that's from an earthquake as well, and that you don't have to be near, obviously, near a building or anything like that for that to be dangerous. These are some pictures of the tsunami wave. Yes, these are real pictures. You can see, look, here's the high-rise building wave coming up here. Pretty impressive. Pretty scary if you were there. Pretty scary if you were right here. If you were right here, pretty much you didn't have a lot of hope of getting out of that safely. The thing about tsunami waves is that as they go through the water themselves, they're not very dangerous. You could actually be in a ship and not even know that one's passed by you. It's where they start coming up onto the continental shelf where it gets shallow around the continents. All of the energy of the wave now can't be absorbed in the water itself, and it starts to, the only place it can go is up. It's not going to get absorbed into the ground because there's not enough time. It's going to go up, and that's why the wave gets taller as it gets closer to the shoreline. You can also have psyche waves, and this is what happens when basically it's the same kind of thing if you had a cup and you were to shake the cup and the water in the cup would shake back and forth. Well, a lake is just basically like Earth's cup, and when the Earth shakes like that, it makes the water in there shake, and then it's going to change the water surface, and you can actually have waves sometimes can come out of the lake that wouldn't normally come out of the lake, or if you're on the water, you might have some issues then as well. Some other things that are dangers when you're looking at earthquakes are, this is like quicksand. Basically, it's called liquefaction, and it's where solid ground can turn into liquid because as it shakes, the water comes up from the water table through the ground itself. And so what you're looking at here is, right here you can see the little water pools in here, but this was an area that was dry first before the earthquake actually happened, and you can see how it cracked the sand in here and allowed the water to come back up through it. It's called liquefaction. So what do you need to do to protect yourself from earthquake dangers? These are, here you can see these were houses down here. And this was a landslide that happened in conjunction with an earthquake. The earth shook, knocked the stuff down. So you need to get underneath something. The safest place in your house is the door because that's where the strongest part of the structure is. So you want to stand there. It's better than being underneath a table or something like that because a lot of times if something's going to fall off the roof, if they're worried about building collapse, it could actually collapse onto the table and trap you underneath the table. The table might collapse, that sort of thing. So, but your best bet is to stay in the doorway. You want to stay away from any glass, that sort of a thing. You want to stay away from, you want to stay away from any gas lines and things that might catch on fire. Earthquake drills. Obviously in schools they can't all be in the doorway, so they're going to be underneath their desks.